Okay, welcome students to this lecture. We are going to study about extreme values of a function. So we start by defining what we mean by absolute minimum and absolute maximum of a function. So definition. So let f be a function with the domain D then f has an absolute maximum value on D at a point C if f of x is less than or equals to f of c for all x in D and has an absolute minimum value in D if f of x is greater than or equals to f of c for all x in D. So after defining, then we know consider that the maximum and minimum so the maximum and minimum values of a function are what are called the extreme values. Of the function f. Absolute maximum or minimum for function are also referred to as global maxima or minimum. So remember, maxima is the plural of maximum value and minimize the plural of minimum value. So then so if you consider, for example, a cosine function, a sine function, and cosine function, minus pi over 2, 0, then pi over 2. So you have negative 1, 1. So this is y, this is x. So this is how the cosine function looks like. And then this is how a sine function looks like. So the black one is the cos function. This other one is the sine function. So this is the maximum value. So this is the maximum. This is also the maximum value of the sine. So what you need to note is that functions with the same defining rule or formula can have different extrema, that the maximum or minimum value depending on the domain. See examples below. So I'm going to draw some sketches for graphs of the same function on different domains to show their values. So for example, if we have function, so in form of a table, function rule, domain, and then absolute, so domain D, absolute extrema on D. So the first we want just to use y equals to x squared as our function, but then we'll define different domains. So B is still y equals to x squared. C is still the same function, y equals to x squared. D, y equals to x squared. So we consider the first domain from negative infinity to positive infinity. And then next domain 0 to 2. Next domain 0 to 2, but 0 is not part of the solution. And then last 0 to 2 without including the endpoints. So the first domain, this function x squared has no absolute maximum, and also it has an absolute minimum. Of 0 at x equals to 0. And then when you define from 0 to 2, absolute maximum of 4 at x equals to 2. And then absolute minimum of 0 at x equals to 0. And then 0 to 2, but not including 0, we have absolute maximum of 4 at x equals to 2, and no absolute minimum for this other one. There's no absolute maximum or minimum. So I can just say no absolute extremum. So we can actually draw the graphs to illustrate what is happening. So for the case A, so draw the graph. So this is the graph of y equals to x squared, where our domain D is from negative infinity to positive infinity. So this is the what you are referring to, the absolute minimum only. So this arm and this arm continues indefinitely in the positive y direction. And then example 2, so we have this graph, the same graph, but then now 2, we have a value supposed to be 4. So it is y equals to x squared. So domain is 0 to 2. So there's this minimum point and then there's this maximum point. So we have absolute maximum and minimum. 0 and then value 4 at x equals to 2. Okay, C, we have the same graph, But then at this point here, no, so the main here is, so remember we have a hole at this point here. Let's draw it properly. The value of the function is not defined at 0. So there's a hole here. So y equals to x squared. So domain 0 to 2. So this y, so this 2 is here, then we have a point. So we have absolute maximum only. There's no point here. C, so we have this D, not C. So the function is not defined at 0. And also when x is 2, the function is not defined. So domain here is this open interval from 0 to 2. So this is the curve y equals to x squared. So no maximum nor minimum. So that's what we have. So it tells you that now the domain of a function determines whether it has a maximum or a minimum. And having the same function does not necessarily mean that they have the same points of maximum and minimum. So theorem, the extreme. So this theorem will help us know whether the function has maximum or a minimum point. The extreme value theorem. So the statement says that if f is continuous, on a closed interval, AB, then f attains both an absolute maximum and an absolute minimum in this closed interval AB. That is to say, there are numbers x1 and x2 in this closed interval AB with f of x1 equals to m, and the function lies between these two values for every other x in this closed interval. So we'll not go into the proof of this theorem because it involves knowledge and real analysis, which is really not necessary for this course. So some possibilities, so let's have some sketches of graphs. So we are going to draw some sketches, which, with the help of the theorem we have stated before, can allow us to know whether the function has a maximum or a minimum point. So the first sketch this is the x-axis, have point B, then we have A. So if we have this graph, so at this point here, so this way you have x2, this way you have x1. So therefore, this is the point x2 comma m, and this is the point x1 comma small m, and then this is the graph y equals to f of x. So here this case shows maximum and minimum points. So remember, this is the minimum and the other one is the maximum. So this shows maximum and minimum points at interior points. We are saying at interior point because there are values between A and B. And then another case, so we have A here, then we have B here, and then so for this case here, this is what is m, this is what is small m. So this is the y equals to f of x. So for this case, we have maximum and minimum at endpoints. So we see the maximum is at A, minimum is at B. Another example, so we have A, then we have B. So we have this. So this is a small m, and then at this point here we have this x2. So this is the y equals to f of x. So this shows a case whereby maximum at interior point and then minimum at endpoint. And then another case, another possibility, we have this. So we have A here, we have B, so this is small m, this is capital M. So for this case, we have a case whereby minimum at interior point maximum at endpoint. Minimum maximum at endpoint, yes. So that is what we have. So let's give another definition. A function f a local maximum. So the keyword here is local maximum. Value at a point C within its domain D if f of x is less than or equals to f of C for all x in D lying in some open interval containing C. And similarly, we say that a function f has a local minimum value at C within its domain if f of x is greater than or equals to f of C for all x in D lying in some open interval containing C. then local extrema, for this to mean local maximum and local minimum are also called relative extrema. So I will draw a sketch to show what we mean by local maximum, local minimum, absolute maximum, and absolute minimum. So consider the graph below. So this curve will help us to understand what we mean by local maximum, local minimum, and absolute maximum and minimum. So let this one to be A. So this is the x-axis. So let this be A, this point be C, this point be E, this point be D, this point be B. So in this graph, A, this point here, let me label this point as A, capital C, capital E, capital D, capital B. So at this point, we can draw a tangent at this point. Can also draw a tangent at this point here. So with those labeling, point A is an absolute minimum since no smaller value of f anywhere also a local maximum, a local minimum. So remember, absolute minimum means a local minimum, but not the other way around. And then C, point C, is a local maximum since no greater value of f nearby. But it is not an absolute maximum point because it in the whole domain of the function is not the only maximum value. So there are other points which are higher than that. Then point E is a local minimum since no smaller value of f nearby. It cannot be called an absolute minimum because there is another point in the domain of the function which is lower than that point. And then point D is an absolute maximum since no greater value of f anywhere. It is also a local maximum. So remember, absolute maximum means a local maximum, but not the other way around. So we're calling it an absolute maximum because it is the highest point in the domain of the function. There's no other point other than point D with a value more than that at point D. And then point B is a local minimum since no smaller value of f nearby. So it's a local minimum but not an absolute minimum because there's another value of the function which is less than that value at point B. But it's a local minimum because around the neighborhood of point B, there is no other value lower than what we have at B. So that is what we have. And then the first derivative test for local extreme values. So this theorem will help us to know how to find some local or maximum values of a function within the closed interval label. So it says that if, so this is a theorem. So if f has a local maximum or minimum value at an interior point, C of its domain, and f prime is defined at C, then f prime at C equals to 0. And then let's define what we mean by critical point. An interior point of the domain of a function f where f prime is 0 or undefined is called the critical point of f. So the key terms here, the critical point, and then f prime is 0 or undefined. So these are the keywords, this definition. Either the derivative of the function is not defined at that point or is 0. So that is what is called a critical point. So how to find the absolute extrema of a continuous function f on a finite closed interval. AB. So we'll pick from here the next session. Thank you.